what do you want to know about number 2? I mean,
we want to know about lab grades. How are those factor in? Is it really out of 1,000? Is it weighted?
It's 1,000 points, and the way you can look at it is in the beginning of the lab manual, there's a table that lists each exercise, and it lists the number of points associated with the exercise. So for instance, lab number 1 has 0 points. Lab number 1 was your opportunity to get some feedback on how you were doing. I don't remember off the top of my head. I know some of the labs are worth more than others. So some of them might be 150 points. Yeah, right? Yeah. The factor that you get is multiplied by the number of points. So let's say a lab is worth 100 points, and you got a 0.9. You'll get 90 out of those 100 points. You can do all the math to add that up along the way, okay? So you can get up to 1,000 points in the lab. In lecture, you can get up to 1,200 points. It's 2, 4, 600 for the 3 exams, plus 600 for the final. And then the extra credit is just all of that, like, extra frosting on top.
On top of what, though? The lecture grade?
On top of every, because basically it all goes into the same pool. So whatever points that Franny will send me a spreadsheet at the end of the day, figure out all the grades. She'll send me all the number of points that you guys have earned in lecture. I'll have all the number of points you've earned in lab, and I'll have all the lecture. And then, the extra credits just added on top of all that. It's not like there's a limit to where it's going to come from.
So say you're doing bad in lab, me, and okay in lecture, but you did all the extra credits. Yeah, whatever. How does this go?
Well, I mean, if you've done all the extra credits and you've done well with them, then you have the potential to make up some of the points that you may have been deficient in lab, or if you didn't do well on an exam. But each person's a case-by-case basis, and you know each other as well. So, I mean, it's hard for me. You can at least begin adding up points to see where you stand. And,
my other question. We didn't, or I don't know if y'all did, get the, did you grade the extra credits yet? Like,
not all
probably
of them.
not. I didn't think so.
Yeah,
it was worth asking,
yeah.
because I've been trying to, gauge, where I'm at and everything like that, but I plan to do well in final exam.
All right. Well, I will say a couple of things. The final is 100% multiple choice, except for the extra credit. Actually, some of the extra credits are also multiple choice. Some of it, yeah.
How many points of extra credit would you say there is?
Part of that will depend. If you've noticed, extra credit on exams, I've kind of used it to people did poorly, let me make it worth a little more.
Yeah.
So I don't, that's why I don't specify. Yeah.
I get you, I got you.
Okay. And that's to your advantage, isn't it?
It definitely is.
You're welcome.
Just gotta do better than everybody else.
Well, I will say this though. It's not an easy exam.
I know.
It's not an easy exam.
It's the whole semester.
I think people tend to be a little overwhelmed by the optical crystallography because you haven't been tested on that yet.
Can you make that number 11?
No, it's
up there.
Fibrous and conoscopic.
Yeah, conoscopic fiber. That's all part of.
Oh, you're right.
All the same thing. Yeah. So it's a lot, and I have not tested you on it yet. Not really, right?
Now you will.
Yeah, now I will. And the photography, I have not yet tested you on that, except with maybe some of the questions from FWS 313, which was, for some of you, it was like a year ago, a year and a half, 2 years ago. It's been a while. So what did she ask in that exam? It's along some of those same ideas, that, like I said, back then those were just concepts. Now you've done all the exercises in the lab to put those concepts into action. We talked about depth of field. Now you've done an exercise in which you've experimented with changing the aperture size and seeing that smaller aperture sizes, nominal focus, nominal exposure for every single one, but smaller aperture sizes at nominal focus give you better depth of field, right?
Sorry, this is a rant. Not really rant, it's completely relevant. I want to say it before I forget. We did the lab and we did the depth of field and we had to alter the angle. Is there a way to quantify the depth of field without looking at the angles, like, is there a magic number for that too, or no? 'Cause we
No,
didn't
I mean, one of the reasons why you were using that ruled grid was because then you can make a measurement. So you started off with nominal, with the ruled grid flat, right? So now you've got a nice image of basically a two-dimensional ruler. And then you started with a large aperture opening, so that after that, you kept it at that large aperture opening and you started tilting it. And what you should have seen in each subsequent photo was that, oh, the stuff on the edges is getting blurrier and blurrier and blurrier. And then you left it at an angle and you began changing the nominal exposure to use smaller aperture stops. And you had to change the shutter speeds to get nominal each time. And as you did that, you should have seen that the original image with an angle, with a large aperture, I get real blurry on the edges, and maybe just the center is in focus. But as I begin to close the aperture at nominal exposure each time, now I can actually almost get a measurement of more and more and more of that angled scale in focus at the same time. So that should have been what you saw, hopefully. And I saw a bunch of you nodding like, yeah, that is what I saw, which meant that, yeah, you kind of hit it on the nail on the head, yeah. Okay?
That was it.
Okay. Okay. So other people can ask questions too.
We made that list as a collective.
Yeah. Okay. So fibers and conoscopic. And someone was mentioning one of the nice things about the moot court, which we've all, I know I'm like 6 hours, even with a lunch break, I'm like, what? That was a long time to devote. But it was also a little bit of review because you saw them testify about everything that you guys have done, right? You've done every single one of those exercises. But I think the main difference was they used a Mettler hot stage instead of mixing liquids for the refractive index of the last experiment, okay? But basically, you did the same exercises or similar exercises. So you actually had a better opportunity to be able to critique what they testified about. I thought for the most part, aside from a little bit of their language and how they articulated things, they were a pretty good bunch. Some of them were real nervous, some of them, because they were so nervous, probably didn't testify as well as they could have. But so with something like a fiber is isotropic or anisotropic? Anisotropic. Thank you, anisotropic, okay? Usually, okay? Some of you have already looked, I'm going to skip around a little bit. Some of you were asking me to help you with getting the focus of glass fiber, right? And that was for the conoscopic exercise. And for those of you who've done that already. So some of the samples for conoscopic included the glass fibers. And glass fibers are glass drawn thin to be like fibers, okay? And in that particular case, it's still considered a fiber by definition, microscopic in size, longer in one dimension than the other two dimensions. And it's not as flexible as some other fibers, but if you took a thin glass fiber like that, you could have a little bit of wiggle before you break it. And being a glass fiber, through the cross polars of a microscope that's appropriately set up for further illumination, how do you think that glass fiber will look when you have your cross polars in place and rotate the stage?
Dark.
All the way through, dark, right? So, but you didn't have glass fibers for your fiber exercise. You had all these other fibers, and for the most part, with the exception of cotton, you saw parallel extinction, which meant that with cross polars, you put your silk, your polyester, your nylon, once again, the only exception being cotton, but only because cotton is twisted, okay? If you were to untwist the cotton, you could probably get to a point where you have parallel extinction, because what you should have seen with cotton is through cross polars on the appropriate setup microscope, as you rotate it, some of it got dark here and got bright there, all right? So that the lack of complete extinction was purely a matter of its being twisted, okay? But otherwise, all those other fibers experienced parallel extinction, which means that if you position the fiber such that the length of the fiber is either along the horizontal crosshair or the vertical crosshair, it'll be completely dark, right? And then you rotate it from that position, it begins to get bright, and maximum brightness is at 45 degrees for that particular situation. So it's anisotropic. The fibers you looked at, which were all fibers used for textiles meaning clothing, meaning rugs, carpets, blankets. I mean, you get that basic idea. That's not weird. That's not out of the ballpark. So you guys were asked, now you learned about things like optic sign, but you did not deal with optic sign when it came to fibers because you're not really able to, a fiber is not a crystal. It's a pseudo-crystal. It's behaving like a crystal. It's definitely anisotropic. It's not, the fiber does not behave the same in every possible orientation when it's on the stage of the microscope, okay? Whereas something that is isotropic like glass, you rotate it, or you can rotate it to the stage or find some other way of rotating it, and it'll appear dark the entire time, okay? So with the fiber, we're not concerned with optic sign for the analyses that you're doing because we can't necessarily get the best idea of the positionings of epsilon and omega. Epsilon and omega being the principal refractive indices, because we're going to look at the fiber as being a uniaxial material. Okay. However, even looking at it as a uniaxial material, it does not necessarily mean that the principal refractive indices are aligned with the length and the width of the fiber. And because they might not be aligned with it, the best we can do is sign of elongation. Which of these directions is the light experiencing a higher refractive index? So that's why we do with sign of elongation instead of optic sign with the fibers. Okay. And back to this idea with epsilon and omega, we're talking about principal refractive indices that you can have, at principal meaning that they basically are, for uniaxial, they denote the lowest and the highest possible values for the refractive index for that material, okay? But the fact of the matter being, lowest, highest, they can have any refractive index in between for epsilon primes. Omega stays the same no matter what because omega is an ordinary ray, so when the polarized light hits it from the bottom, you know, it's coming from the bottom of the microscope, hits the fiber will split into two mutually perpendicular vibrational modes, and one of those modes will be experiencing the omega refractive index. The one that's perpendicular to it will be experiencing either epsilon or an epsilon prime, depending on the orientation of these things. Okay, so because you've got two mutually perpendicular vibrational modes, and that's one of the tricky things about when you're thinking about these indicatrix figures, it's that refractive index and its vibrational mode. Because one of the things I noticed today at testimony, one of the fiber experts talked about the fiber as if the light is traveling, the refractive index related to the direction of travel. The light is traveling from the bottom of the microscope up towards your eyes, but the refractive index and the indicatrix figures are referring to the vibrational modes. So the light's traveling up, but it's vibrating this way, or it's vibrating that way, or maybe something in between, whatever the case may be. But we need to start thinking about that vibrational mode as, you know, is it vibrating side to side, east, west? Is it vibrating up and down, north, south? Okay, so it's vibrational modes. Because the indicatrix figures, when we're looking at those indicatrix figures, the diameters of the ellipses are the direction for the major diameter and the minor diameter are the directions of vibration, okay? Which is the reason why I would like pick up one of these things and I'd say, okay, it's got that one little, it's got one metal rod through it, must be uniaxial, that's the axis. But I want to think about this in terms of this represents a crystal on the stage of the microscope. In this particular position, I've got my circle, the teal circle. If it's a circle, it must be representing the magnitude of omega, okay, because it's the same diameter, which means like omega doesn't change. So I think of it as it's on the stage of my microscope and light's coming through from the polarizer, and that light's only vibrating side to side, and then it'll only be experiencing omega, okay? So by the time it gets up there, it's going to get blocked, okay, and it'll appear dark, okay? And then you start doing weird things like, what if it's something different? Then it can experience, epsilon primes as well, or epsilon, and you have a situation where you're going to get, light emerging from the analyzer. So with the fibers, you saw the retardation colors when you had the fiber in a position of maximum brightness, and you needed to diagnose, like, well, what's the retardation, so I can make a measurement of the optical, which is a physical property of the fiber, what's its birefringence. And remember, birefringence is related to the thickness of the fiber, as well as basically the birefringence is the difference between epsilon and omega, okay? But the retardation you see will depend on how thick that fiber is. So one of the things, I don't know if I have it over here, but if you took two nylon fibers and they were identical in chemistry, and those two nylon fibers, one was, twice as thick as the other one, and they were both cylindrical, let's say, okay? What it would mean is that the one that was twice as thick would have twice as much retardation occurring because the light went through twice as much of that sample, especially in the middle of it, right? And you also have, because it's cylindrical, the thickest part of the sample is right in the center, so when light's coming from the bottom of the microscope, the light that went through the center of the fiber went through more of the fiber than the light that went through at one of the edges, and so you'll see a different retardation color, because remember, that's why the retardation color is related to the thickness. Okay, so that's why you needed to make a measurement of the thickness, because you needed that information as well as the retardation color in order to determine the birefringence of that particular fiber. Sign of elongation, basically, you're trying to determine whether or not the higher refractive index or the slower ray, is it vibrating along the length of the fiber, or is it vibrating along the width of the fiber, perpendicular to the light, okay? And the way to do that is by using those compensators to see the direction that the retardation is heading. When you get more retardation when you put in a compensator, it's additive. More retardation means that I'm looking at my Michel-Levy chart, and the color that I'm seeing goes from whatever color it started with, but it heads to the right. Okay, that means I added retardation to it. If, on the other hand, and it's all based on orientation, because in one orientation it'll be additive, and then you rotate it, and now 90 degrees it's subtractive in this. So changing the orientation is sufficient to change whether you're getting subtractive or additive retardation. So if you're starting with a particular color and the fiber is oriented in a particular way, whatever color you see, and you put in your 530 compensator, and now instead of going that way, it goes 530 in this direction, that means you got subtractive retardation. But basically that gives you an opportunity for understanding if the slow ray that's being experienced by the light rays going through the fiber, if it's aligned along the length of the fiber or perpendicular to that. Does that make sense? Do I have your diagrams? Or?
No.
Yeah?
I mean, no, you don't need to draw.
I
I do have a question though. For the test, should we bring a Michel-Levy chart, or do we not need one? Or
You should not need a Michel-Levy chart. I mean, I guess I'll bring one if you want. But you won't be. You need to understand how the Michel-Levy chart works.
Calculating things.
Yeah, you will need to calculate things, but you'll be given clues as to how. I already gave you this clue. I'll give it to you one more time because you were so kind enough to suffer through 6 hours of moot court. Remember I talked about how when you look at your conoscopic image, it's the same idea. If there's thicker sample, it's more retardation. But how that looks on iconoscopic images, more and more of these fringes of color. So for a uniaxial material, if it's properly oriented, and properly oriented for iconoscopic means that the axis, optical axis is aligned with the illumination path of the microscope. If it's properly oriented, if I have a thin sample of sodium nitrite, I'll just get maybe a couple of circles of color. And those circles of color, their gradation is exactly Michel-Levy. Right? You get the black cross in the middle, and then as you, if you start from the center of that black cross and take a radius out of it, you'll start, basically you're getting a Michel-Levy chart. Black at the center with the cross, and then just outside of it, you start getting those grayish colors, and then you get low order white, and then you get like a yellow, orangish, yellowish, and then you get first order red, and then you get that pretty blue color, and then you head to higher orders, and eventually you get to high order white. But if it's a thin sample, you might only get maybe one order's worth, or maybe 2 orders worth of Michel-Levy colors. If you have the exact same material, let's say sodium nitrite, but it's 3 times thicker, then you will get many more circles of color. And same idea, you start at the center, it's black, and then just outside of the center, you get your gray color, then your low order white, and then you get to first order white, first order red, second order red, third order red. And you can think of those reds as each being like the 530 to 550. So this first order red is 550 nanometers of retardation. The second order red will be 1100. And so you know how to multiply 550 by a number. You'll have your calculator to do that. So you can figure out the total amount of retardation if you're given an estimate of the number of orders of red that are visible. Okay? So you can make an estimation of that. The other aspect of that is that when you're working with a conoscopic image, things like, if you understood the idea of the positioning, this is more applicable for the biaxial materials. And once again, the positioning of the material is critical. If you don't have the crystal positioned on the stage of the microscope, so how many of you had an opportunity to look at the standards for the conoscopic, right? So you saw crystals that were like, Jesus, I can't see a well-positioned crystal, and the reason why was because they were not oriented in such a way that you would get that. So I already mentioned, for uniaxial, to get a centered uniaxial interference figure, they have to be positioned so that the optic axis is aligned with the direction that the light is moving through the microscope, like this. And if they're like that, or something else, you're going to see something weird. You're going to see something, if it's just a little bit off, like this, here's my optic axis, and instead of being straight up and down where the light's going through, it's a little off. Then what you'll see instead is the cross, but it'll just be doing this as you rotate the sample on the stage. But once it gets a little crazy, then it's like you're seeing black brushes going here and there, but it's hard to tell what's going on. When it comes to the biaxial, you have 2 axes, but the thing that you want to have aligned with the light path of the microscope is the acute bisectrix. Okay? If you have the acute bisectrix aligned with the path of light in the microscope, then you will have a centered biaxial conoscopic interference figure. The one where in some positions it'll look like a cross. And biaxial materials, even when it looks like a cross, usually one arm of the cross will be thicker than the other arm. Okay? If you have a very small optic angle for that biaxial material, then the 2 crosses will appear similar in terms of their thickness. But if you have a very wide optic angle, you'll have like a real thick cross, one thick arm, and the other one will look thinner. Okay? It's just a matter of the optical properties of those materials. But so for both of these, these are biaxial materials, and in this position on the microscope, the acute bisectrix is aligned with the path of the light. And because of that, you should be able to see a centered interference figure that, which when you rotate, will give you your, starts with the cross, you rotate it, and then you get these brushes, those isogyres that spread out, let's say in the first and third quadrant, and they come back together as a cross, and you keep turning in the same direction. Now they'll spread out in the second and fourth quadrant, and they'll keep doing that kind of thing, okay? But if you have an understanding, and like at some point, you guys should be able to come up, if you haven't already done so, you should look at these things and feel them and look at them in terms of, okay, I've got like a red ellipse, I've got a yellow ellipse, I've got a dark blue ellipse, and the major and minor diameters of each of these ellipses are representations of alpha, beta, and gamma. And because what we talked about were diameter of the major diameter, minor diameters, the longest major diameter is going to represent the largest refractive index. And the largest refractive index in a biaxial material is gamma. Okay. The shortest one is going to be representing the magnitude of alpha, and the one that's in between is going to represent the magnitude of beta. So, Gesundheit. So we talked about the yellow being the ellipse, which represents having both the gamma index, the longest refractive index, and the alpha, the shortest refractive index. Okay. But bear in mind that the ellipses will either be alpha gamma, beta gamma, or beta alpha. It's like XY, YZ, or XZ. Okay, those are the three principal refractive indices. When you get this concept down, you'll see that the optic axes represent the lines in the optic axial plane, where you have gamma and alpha. Those axes are the lines that are perpendicular to a circular section in my indicatrix figure. So you do have circular sections in your biaxial indicatrix figures. Whenever you have a circular section, like you have a circular section in your uniaxial, but remember that represented omega, right? Over here, what does my circular section represent? It actually represents the value of beta. So the idea was that if I have my alpha value, the shortest diameter, I have my gamma value, the longest diameter, that somewhere in between this value and that value is intermediary beta, okay? And this teal-colored material, it's my circle, this represents the value of beta, and what you'll see is that the thing that I'm pointing at over here, it has the same diameter as, beta, right? Because this was gamma, and this is longer than alpha, it's beta. Okay, so this particular section is a circular section. It happens to be one possibility where if you had your sample, your crystal oriented on the stage of your microscope such that an optic axis was aligned with the way the light is moving through the microscope, it would only experience beta, okay, the beta index. And so it'll appear isotropic.
Why?
Because it's only experiencing one refractive index, which is kind of like what happens with isotropic materials. Now glass is isotropic. It's not isotropic because it's perfectly symmetrical. It's isotropic because it's very random. It's like, you melted the crystal and then you cooled it down so quick it didn't have a chance to like line up into a crystal lattice, and now there's like this jumble of molecules, silicon dioxide molecules and whatever else is in there. And that's what makes it isotropic. The other kind of isotropic is what we talked about in symmetry, continuum. The most symmetric was cubic, right? So with the cubic crystal system, it's isotropic, not because it's all jumbled, but it's the most organized of all of the possible crystal structures because all the atoms that are aligned in that crystal lattice, the distance of the bonds is this exact same, which means all the atoms are the exact same distance away from each other, okay? And all the bond angles are 90 degrees. And that's what you have with sodium chloride. So if you took sodium chloride and a piece of glass and put them both on a slide, threw them under the microscope, and you put in your analyzer and you rotated it, it would look dark all the way through, but for different reasons. The cubic, because it's perfectly symmetrical. The glass, because of the random orientation, but they're both isotropic. Okay. The glass is isotropic. The cubic crystal is isotropic, but it's also isometric. Iso meaning the same. So isometric means same measurements. So all three dimensions, length, width, and height, are the same in the cubic material. So it's isometric and isotropic. Okay.
So wait, so when you oriented it like that, and you said it's experiencing beta, is it because the light's traveling is perpendicular to beta in that orientation? Is that why it would only
The
experience
light
beta?
is experiencing the beta refractive index. That's what's happening.
But why only the beta?
Because in that particular orientation of the crystal, no matter how you rotate it, there's a circle over here.
Mm-hmm.
It represents the magnitude of the refractive index that's being experienced. That's beta no matter how you rotate it. If it only experiences one refractive index, then it looks like it's isotropic. Okay, do you want to take a closer look at these circular sections that I'm talking about? Like I said, these guys are pretty sturdy. Don't toss them around, don't throw them on the ground, but do you see these circles that are in here?
I do.
Yeah, right?
But I was just wondering, is it because it's perpendicular? Why wouldn't it experience? I mean, if you had it oriented like this, I see that the beta one that my fingers are on is the only one that's
Yeah, so your fingers are on that,
Yeah.
and now think of the light coming from the bottom,
yeah.
and it's experiencing
Oh.
this refractive index. But
Oh.
rotate it,
I know what you mean now.
and now it's also still experiencing beta. Because if you think of this circle as being flat on the stage of the microscope, the diameter is constant as you rotate it, which means the refractive index is constant as you rotate it, which means only one refractive index is being experienced. And if only one refractive index is being experienced, then it looks like it's isotropic. I mean, do you guys want to see? Kind of. This helps more if you look at it and feel it and see, oh yeah, that is a circle. Because over there, you're like, what freaking circle? Right? It's like, I don't see a circle. I see some multicolored pretty things, but I can kind of see that this is an ellipse. That's an ellipse. And this blue ellipse is hard to see because the teal circles are obscuring them. But when you begin to actually see them, then imagine that circle representing the beta index is flat against the stage, and then no matter how you rotate it, the only index being experienced is beta. Okay.
I have a question, another one. Where is the acute bisectrix on that?
The acute bisectrix on this, well, the black lines represent the optic axes, and remember the optic axes are perpendicular to that circular section. Okay. It's in some ways, basically the optic axis defines that an optic axis or uniaxial means that this one line and the omega is going to be perpendicular to that. So the circular section, the uniaxial, is this teal color. And if I have my crystal positioned like this on the microscope, it'll only experience omega no matter how I rotate it. It's changed if I have my red ellipse. If my red ellipse is flat on the stage of the microscope, which means my crystal is on a glass slide like that, then light will come up from the bottom, and over here it'll experience
The red one.
epsilon,
Yeah.
but I'll rotate it. Now it's epsilon prime, epsilon prime, epsilon prime, epsilon prime. Oh, now it's experiencing omega,
Yeah,
because
yeah, at the same time.
the smallest diameter on my ellipse is also the diameter of my circle. Okay. So you can look at it and think of it that way. But one of the things I also want you guys to keep in mind is that when you examine a crystal, I think I mentioned this in lecture and definitely in the lab, you always start orthoscopically. It's like just because it's a conoscopic exercise doesn't mean that I'll set up the microscope, I'll put it in the Bertrand lens, and I'll throw a sample on the stage, because you have to see what the sample looks like first orthoscopically. Where is the crystal? Is it in focus or is it out of focus? Because if it's out of focus, let me change the height of the stage. So you've already set up your microscope for curler illumination. You don't have to have the analyzer in. You should not put the Bertrand lens in yet. Put your sample on the stage of the microscope and start with low power, because you don't want to spend a million years hunting around where is that crystal of interest. Low power, okay, there it is. It's fairly well focused. Let me put it in the center of the crosshairs. Pop up to the higher objective lens, magnification. Refine the focus, maybe recenter a little bit more until I get to the highest power objective, in which case I'll have a high-powered view of the crystal of interest. And now I'm ready to, I mean, you could have done this before, but now I'm ready to put in my analyzer and rotate and see, okay, it's dark, now it's getting bright, now it's dark again, now it's bright. Okay, now I'm ready to put in my Bertrand lens. So you never start conoscopically. Whenever you're doing any kind of work, you start with the basics of microscopy like you learned in FOS 313, where you should always start with the lowest power, because if you start with a higher power, then you might be wasting quite a bit of time. Where is my sample? It's totally out of focus, and it may be off at some periphery over there, but if I'm trying to identify its position in space, and I already have a sample magnified 100 times, then this little fiber is like, it's, you know, the whole slide, if you want to think of it that way, is 100 times the area, and where the hell am I going to find it? So start low power, so you can find, and like I said, simple common sense things like, oh, there's a squiggly thing, okay, it's right over there. Let me put that part of the slide right over the circle of light coming through the microscope, so I don't have to waste a lot of time finding it. I mean, you don't want to put things down blindly and then have to hunt through the oculars. You have a concept of where you want to begin. Now that you've gotten a focused sample, and you have your analyzer in, and you have your Bertrand lens in, now you're able to see, hopefully, a centered biaxial or uniaxial interference figure. And then you can start using your compensators to figure out, okay, you know, is it a positive optic sign or negative optic sign, that sort of thing.
So from practicing with the standards, there were some things that I noticed. What are those things called?
Isodryers,
Yeah.
brushes.
Yeah, so I noticed that some of, I don't know if the unknowns will be super clear or what, but like it wasn't very clear on how, where to measure from to get the optic angle, because it was like, you would see like dark lines, but then there would be so much blurriness, like you start at the end of the blurry.
Well, a couple of things.
You have tips?
With the Bertrand lens, there's a focus,
It
so you
didn't
could
help that
adjust
much.
that.
It didn't really help, yeah, that's.
No.
Yeah, it
No.
was like,
It was just like, you know where it was the darkest, and it's kind of like expanded like that.
Yeah.
So it was just
Yeah.
like,
I
where
would
do
take a
you?
step back and
Big
go
space.
back to orthoscopic to make sure your crystal's
there was
focused
like
as well.
4 micas, and like there was one that was like really good. The other one.
Yeah, the micas are all
Yeah. Those ones
really easy to see because they're pre-oriented.
Yeah.
Micas are by nature flat sheets of minerals, and you can have a thick, like several sheets of those minerals, or you can peel away a thin little one and have a much thinner section of mica. But because it's a sheet, you're not going to put the sheet on the slide like this and then put a cover glass on it and smush it. It's going to fit best if the sheet's against the largest surface area of the sheet is against the largest surface area of the slide, then you put your cover glass over it. And so those are the nicest samples because you don't have to do a lot of work to orient them. But I will let you know that for your conoscopic practicals, you will not need to orient the samples that you're working with. They will be pre-oriented. So it's just a matter of, you know, getting the conoscopic image and making the measurements of concern. So you will not have to worry about getting them in the correct orientation. Okay. Let's see. Did I move too fast beyond fibers? Do Do you have questions about fibers? You're good. Now with conoscopic, some of the things I was alluding to was the idea that I think making determinations of optic sign on uniaxial is a little simpler, but do you have questions about how to do that? You've got your black cloths, and like I said, you insert one of the compensators, and everything shifts. You use a 530 compensator, everything's going to shift by 530. So what was black will now turn magenta, because it'll shift 530 over. But then everything else, if you start in the Michel-Levy chart, every single thing will shift over by 530, either additive or subtractive. Depends on which quadrant of that Maltese cross that you're looking at. So the basic idea is you need to memorize and put on your little index card that epsilon vibrates radially and omega vibrates tangentially. So it means that in the second and fourth quadrants, tangential to the circles that you're seeing will be omega vibrational modes, and epsilon will be perpendicular to that. If we're looking at the first and the third quadrant, well, if I connect and make a radius out of that, then that's epsilon vibrating, tangential to radially.
Sorry, can you draw a picture of that on the board?
Sure. And this is directly from your from the lecture. So this is radial, so this will be an epsilon prime, let's say, and this is omega because it's tangential. But over here, this is radial because if you extended it, it would go to the center. Okay, if that's radial, then this is an epsilon prime, and tangential would be an omega. So notice how if this line is parallel with this line, this one is radial, but this one's tangential just because by virtue of the different quadrants that they're in. This one's epsilon, but that's omega. Okay, so radial got to be epsilon prime. Perpendicular to that got to be omega, which happens to be also tangential. Radial, and radial, like I said, coming out from the center of the circle is a radius. That's what makes it radial. Epsilon prime, and then perpendicular to that, and omega. So the behavior is the same in the first and the third quadrant, where you have omega vibrating in this direction for both of those guys, and epsilon prime is vibrating radial for both of those guys. And remember, we always have our slow ray of our compensator. Okay, that's what we call it, the Z, or the direction that gamma vibrates in. So basically, we want to compare what's happening here and here, or we can also think about what's happening here and here. They'll just be different. What's happening over here will be different from what's happening over there, because epsilon's over there and omega's over there, but these two things are aligned with the slow ray of the compensator. Okay, and we could be looking at here or here. But whatever we see over here, we should see over here as well. So if I see a blue, if I put in my first order compensator and my cross turned black to magenta, then what was gray before, if I'm getting additive retardation, the gray will turn blue. Okay, if I'm getting subtractive retardation, the gray will turn to yellow. So, but I'm looking specifically over here what was originally that steel gray color.
So you're looking for the color change in the center?
Yes.
Oh.
Oh, all the colors will change. Okay, so let's give an example over here. Let's say that epsilon is greater than omega. That means positive optic signs. Okay, positive optic sign. That means epsilon's a slow ray. Epsilon's a slow ray. So if we're talking about these epsilon's a slow ray over here, but the epsilon's vibrating perpendicular to the slow ray of the compensator in the second and fourth quadrant. Okay. So in the first and the third quadrant, the slow ray is aligned with the slow ray of the crystal is aligned with the slow ray of the compensator. And if I get slow with slow, I get additive, which means that black will go to magenta with the 530 compensator, and gray will go to blue over here. But meanwhile, in these other quadrants, just outside of the magenta cross, gray will go to yellow. But if you really wanted to, you can look at all the other colors and see that, okay, my first order red turned to second order red. That kind of thing. Every single color in the first and the third quadrant will be added by 530. Okay. On the other side of it, in the second and fourth quadrant over here, I have omega aligned with my slow ray. And if it's a positive optic sign, omega is the fast ray. If I have fast aligned with slow, I'm going to get subtractive retardation, which means that every single color over here is going to head to the left in the Michel-Levy chart. So if I started with black, I'll still get magenta, because 530 from black in a negative direction still gives me magenta. But if I started with steel gray, then I got to cross past the black before I get not all the way to first order red. It'll look like yellow color. Okay, so every single color over here will shift negatively by 530, subtractively. Every single color in the first and third quadrant will shift additively 530, if that's a compensator I'm using. If you want to use a 147 compensator, it's the same idea, but instead of adding or subtracting 530, you're adding or subtracting 147. Okay. Now,
when omega is aligned with the slow ray, that is subtractive.
in this situation only, I was about to ask if you could understand now, if I change gears, and now I'm talking about a negative optic sign, where epsilon is smaller than omega. Now, omega is a slow ray, and epsilon is a fast ray, by definition. Okay? And then everything I just talked about would be different. Well, first of all, the black will still go to magenta for the cross, okay? Because I'm either adding 530 or subtracting 530 from black. And if you look at the Michel-Levy chart, I deliberately showed you the symmetric Michel-Levy chart in lecture, which showed you, in class you just get the black and then you go all the additive colors. But the one I showed in the class also showed you that, oh, on the other side, it's a symmetrical thing happening. So I still have, if I have black and I go 530 that way, I'm still going to get magenta 530 from black, okay? What you're looking to see is the actual numerical differences in the retardations and how they'll affect where you start and where you'll end up with. So if instead of the positive optic sign, now I've got a crystal that has a negative optic sign, if epsilon smaller than omega, in this case negative optic sign, then this is the slow ray, and this is the fast ray. Okay. If that's the case, then epsilon's the fast ray in the first and the third quadrant. If I have the fast ray aligned with the slow ray of the compensator, additive or subtractive? Fast or slow? Thank you. Subtractive retardation. So that means black will still turn magenta. That hasn't changed. But over here, if I'm getting subtractive retardation, what was originally that steel gray color, if I have to head to the left of the Michel-Levy chart, I have to cross that black region again, 530 over, and when I do get 530 nanometers over to the other side, I'll only have gone so far as to get to that yellow color. Meanwhile, I've got omega is my slow ray. So in this quadrant and this quadrant, quadrants 2 and 4, omega is aligned with the slow ray of the compensator. So if I have slow, slow with slow, I get additive retardation. Same idea, I can add 530 to black, I'll still get magenta for my cross, but in these areas, my gray will turn to blue, because it's starting with Michel-Levy chart, the black goes to magenta, but the gray part, I add 530 to that, and I get a really bright blue color that's very easy to see. Okay. So that's what you're looking for with those determinations. Does that make more sense?
Yes, and no. Yes, because I get the concept of how everything changes. My question though is so E is not always fast and omega is not always slow, right?
Correct.
But what's true is what you drew there, that E prime is
Epsilon.
always radial